We present to your attention research on the topic information protection and recovery Hamming codes-based hash technique. Authors Inna Rozlomii, Andrei Yermilko, Sergei Mitsenko and Sergei Naumenko. Currently, users of many information systems are faced with the task of protecting the data processed by them. Of the measures to ensure data security in such systems is to protect their integrity. Solving the problem of data integrity protection in particularly relevant in functions data processing centers that include storage systems. These systems have different construction structures and operating principles that provide for operating in the conditions of random errors and destructive influences of any untreated. In addition to data integrity control, it's also necessary to ensure the recovery of data whose integrity has been violated. There are various methods of solving the task of control and ensuring data integrity. Among them, schemes of hash functions are of the most significant interest. They are successfully used in the localization of defective blocks, but they are not without drawbacks. The main one is high redundancy when monitoring the integrity of sequences of small message blocks, considering the maintenance shortcoming of the existing solutions. It's urgent to find ways to reduce the redundancy introduced for a given level of data security in the conditions of random errors and destructive influences of the attackers. The goal of the study is a development method for information protection and recovery based on the Hamming codes. There are several types of error correction codes that are used for detecting and correcting errors in data transmission. The first one, Hamming codes. They are among of the most common error correction codes. They allow for detecting and correction of one or more single-bit errors in transmitted data. Hamming codes are used in many systems to ensure data integrity and reliability during transmission. The second one, BCH codes are widely used error correction codes in many communication systems. They are capable of detection and correction of multiple errors, including both single and multiple errors. BCH codes are typically used in systems with low noise levels or on channels with a high probability of errors. The third one, Reed-Solomon codes. They are powerful error correction codes capable of detection and correction errors in data blocks of any size. They are widely used in digital communications, magnetic storage devices, supercomputers, and other systems where data transmission reliability is critical. The fourth one, low-density parity check codes. These codes are used in modern communication standards such as Wi-Fi, satellite communication, and mobile networks. And the last one, turbo codes. They are among the most powerful error correction codes used in modern communication systems. They are based on the principle of iterative decoding, which ensures high error correction capability. In this research, the choice of Hamming codes as a method for information protection and recovery is based on several key factors. The first one, error correction efficiency. Hamming codes have the property of detection and correction single-bit errors in transmitted data. This makes them effective for error protection in communication systems where data integrity is critical. The second one, simplicity and low communication complexity. Hamming codes have a simple structure and are easily implemented. The algorithms for error detection and correction in Hamming codes are relatively simple, allowing for easy integration into resource-constrained systems such as embedded systems and IoT devices. The third one, flexibility. Hamming codes can be adapted to different requirements and application scenarios. They can have various levels of error correction dependency on the system needs. This allows for the use of Hamming codes based on the specific level of protection required for the information resources. And the last one, application in resource-constrained systems. Hamming codes demonstrate good efficiency in resource-constrained systems such as embedded systems, and IoT devices. They don't require large memory capacity or high computational power, making them suitable for use in such systems. Let us take a closer look at each option for calculating the hash function. For this, we introduce the notation H hash function, BI information block, K total number of blocks, N number of hash functions. First scheme shows calculation of a common hash function for K blocks. Second scheme shows calculation a hash function for each block. Third scheme shows calculation a hash function for groups of blocks. Adding of redundant information into the information transmitted by the network provides the possibility of detection and correction errors on the side of the recipient of the message. Adding of redundancy makes it possible to detect and correct errors in the information that is transmitted and can be changed during transmission. There are codes that detect errors and correction codes that, in addition to detection and error, correct it. The easiest way to detect errors are checksumming and pairing checking. The proposed method of data integrity control uses a system of hash codes. They are built according to rules similar to the rules for building linear retention codes. In this case, according to the rules of construction Hamming codes. To control and ensure message integrity B, it must be represented as a set of fixed length blocks B1, B2 till Bn. Blocks are interpreted as a sequence of n information blocks to which as control blocks are added in the amount necessary to protect data integrity. As a result, a code sequence will be obtained shown on this slide. The addition of control blocks is performed according to the rules for building redundant codes depending on the need for correction properties of the received code shown on the current slide. To construct anti-interference resist code message A, we will use the theory of linearly independence vectors, which is used in vector theory to construct a Hamming code. To control the integrity of protected data, block the syndrome is calculated, what corresponds to the predicted. Previous slide shows the result of the integrity violations in a protected data block. Developed linear hash codes built by analogy with Hamming codes, allowing correction errors in message blocks. Still, the number of mistakes that can be received depends on the size of the redundant code. It's necessary to routinely choose the necessary redundant code to ensure, on the one hand, the required reliability of the information and, on the other hand, to avoid burdering the communication channels with a large amount of redundant data. A cryptographic hashing method based on Hamming codes for information protection and recovery was proposed. The main advantage of the proposed method is implementation of information integrity control and detect correction for a given level of security with minimal redundancy and the possibility of localization, integrity, violations, and correction of a given number of errors. The obtained results provide a scientific and engineering toolkit for monitoring and ensuring data integrity, with the possibility of checking the artifact after restoring in case of integrity violating, and provides the conditions for creation, promising and improving existing data storage systems. Thank you for your attention.